Hello, everyone. This is a brief discussion on single replacement reactions. Whenever working with single replacement reactions, we have to be mindful of the activity series for either metals or nonmetals. An activity series is just the list of elements in order of most reactive to least reactive. In this case, for this problem, we want to ask ourselves, is Ag reactive enough to replace K? If Ag is one of the least reactive metals in this series, and K is a very reactive metal, this replacement is not likely, therefore there's no reaction here. If we look further to this problem, we have the question of, will zinc be reactive enough to replace silver? The answer is yes, because zinc, which is right here, this metal is more reactive than silver, which is here. Therefore, this reaction occurs, and we have the balanced reaction as seen over here. Right? This becomes our balanced reaction. Right? If anyone has any questions, please reach out to me via email and I'll provide clarification. This did need to be balanced using previously discussed methods for balancing using stoichiometry. Now, if we go on to the next problem, here we're dealing with nonmetals that are capable of participating in single displacement reactions. So here the question is, will F2, which is by itself, replace K from Ki? Or potassium from potassium iodide, which are ionically bonded. So in this case, we're going to have to look at the activity series for nonmetals to determine if this displacement is energetically favorable. If fluorine is highly reactive, more so, if fluorine is more reactive than iodine here, the fluorine replaces the iodine, not fluorine replaces the K, because we're comparing two nonmetals, fluorine and iodine. If iodine is the least reactive metal, fluorine does have the ability to replace it, and this replacement is energetically favorable. So now we have potassium fluoride and iodine. This would be the balanced chemical reaction with the appropriate coefficients. Notice that now the number of atoms of each kind is the same on both sides. We have two fluorines here, two fluorines here, two potassiums here, two potassiums here, two iodines here, and two iodines here. So now let's go on to the next one. Okay, so this deals with, we're asking ourselves, is copper reactive enough to replace iron from iron to sulfate? So to answer this question, we have to ask ourselves, okay, we're dealing with two metals, right? Copper and iron. This is the activity series for metals. So let's find copper. Copper is going to be right here. Iron is going to be here, higher in the activity series. Iron is more reactive than copper. Therefore, copper does not have the ability to replace iron, so there's an R or no reaction. Let's go on to the next problem. If we look at number 5, we're dealing with, does iron, which is by itself, does it have the power to replace lead? So we have to consult the activity series for metals. We have to find iron, which is here, right somewhere in the middle, and Pb, which is closer towards the least reactive end. So Fe does have the power to replace Pb. This is energetically favorable. So we'd have iron nitrate being formed, and lead becomes displaced. When we do stoichiometric analyses, we see that we have equal numbers of atoms on both sides of the reaction arrow, and no coefficients are needed to be put into these blank spots to make the reaction balanced and make it obey the law of mass conservation. So now we're going on to this next problem. And our question is copper reactive enough to replace aluminum? So we have copper. Can it replace aluminum? So we look at the activity series for metals. Copper is here, closer to the least reactive side. Aluminum is closer to the most reactive side. Aluminum is more reactive than copper. Therefore, copper does not have the ability to replace aluminum. This is energetically unfavorable, and this is a no reaction. So just remember that it takes energy to break bonds. Those are considered endothermic processes, and energy is released when new bonds are formed. That's an exothermic process. So here, the amount of energy that is required to make this happen is energetically unfavorable. So there's no reaction here. So next we're going into this last problem. So here we're asking ourselves, can aluminum, which is here, is this metal reactive enough to replace lead? We don't know unless we look at the activity series. So aluminum is right here, closer to the most reactive side. Lead is closer to the least reactive side. Aluminum is more reactive than lead, right? Because it's closer to the most reactive end here. So aluminum does replace lead to form aluminum nitrate, and then lead is by itself. This is lead 3 nitrate. This is how we would balance everything. So first we take note of how many atoms there are to begin with. Then we add the appropriate coefficients to make the numbers of atoms on both sides equal. So if anyone has any questions, this was just a brief review of how to approach single replacement reactions. Please email me as soon as possible, and I will provide you with the needed assistance. Thank you. Have a good rest of the week.